everybody go ahead and kind of look over your introduction. Make sure you can figure out where the different bits are written for your intro. Okay. I'm going to try and make this a little bit bigger. Okay. So everyone should have a diagram that looks similar to this. And what's nice about this diagram is it traces what's happening with the catapult from, setup to release to the marble becoming a projectile and being thrown. Okay. These are the 4 different parts of the physical interactions that you should be explaining in your introduction. All right. So we have 2 hypotheses. Zach, generally, what's your first hypothesis about? Cool. Yeah. So you're saying, you're making the claim, I can make a precise catapult. Catapult here somewhere, and then you add details to both justify your claim, make percent prediction, and define precision in terms of your catapult. In terms of catapult firing range setup.
Wait, so Jared, we are just for the hypothesis, we just estimate like my catapult can shoot the object 10 feet. Like that would be it.
No. So Brooke, like what you're saying, justifying would be, I think I can set up a shot. So this is the part, Ryan, where you have to like set it up and make sure your catapult works this way, right? So like it'd be something like mine where I said, if I put a target 298 centimeters in front of my catapult and fire the catapult 20 times at the target, I think I can hit the target 80% of the time if the target's 19 centimeters by 20 centimeters by whatever centimeters, right? If you shot into it. And the reason why I think this is because I set my catapult up and measured where most of the shots tended to go. And I found something that it seemed that the catapult could reliably hit over and over. You catch that, Ryan and Brooke? You said you got it, right?
Yeah.
Does that make sense, Ryan?
Yeah.
Cool. And then your general hypothesis too, Leo, is saying what?
Second catapult and how much more accurate it'll be.
Yeah, or precise, right? I can make my catapult more precise by, and then here you say what you're going to change, say what you change, and you kind of defend your claim by basically saying how what you changed should make it better given what you observed in your first set of trials. Yeah. Explaining, defend your claim by explaining how the first trials flew and how your fix will improve. Okay, and then of course, again, you're going to make a percent hit prediction, and this one should be better than hypo 1. Yes, Zach.
Let's say in your hypothesis, in the second hypothesis, can you like lower that prediction if you think will be more accurate?
No. You have to try to make it better. Oh, you mean okay? So you mean hold on? You're saying like I said I was going to be 50% precise, but actually I was 20% precise. Now my second set of trials, you know, I'm not comfortable saying better than 50% or something. Yeah, that's fine. As long as your prediction is better than the actual results of your first catapult. But courage will be honored and respected always. So there's no loss to saying to shooting for 90% or even like 95%, right? You cannot lose, because if you lose, you still do well, right? If you shoot for 30% or 50%, and you miss, I feel like it feels worse. I'd rather shoot for 100% and hit 20% myself than not ever try. That's me now, though. I actually wasn't like that when I was your age.
It's realism versus optimism.
Yeah, I'm pretty optimistic. But let's get back to the intro.
Wait, Jared, do
Yes.
we do our data before making the first hypothesis?
No, but you do mess around with the catapult a bit
Oh, okay, cool.
to make it. Then after you do that, mess around with it, make your hypo, then you collect your data. All right. Next step. Okay, so Nico, what's something you defined in this introduction? Wait, hold on, slow down. Don't say everything. I'm gonna ask other people. So elastic potential energy, kinetic energy. You said force generally. And y'all, at this point in my class, if you list these definitions, I'm giving you 0 credit for it. It should be nested in a paragraph that explains what you're doing, okay? That's literally been the requirement all year. This is the final. You must meet the requirement.
Would it be all right if we nested it, but then also left the definitions below?
No, I just want to see each definition once.
So you also have to define what a catapult is, like an energy converter, that first potential energy.
Yeah, but that could be written as, so you have to connect these to a catapult, right? So these would be,
I guess that's more of what I did. I just want
okay. So we're connecting this to a catapult's function, right? Elastic potential energy. So we said, and if we look at this drawing right here, this drawing right here is showing, let's see if this is going to work. No, it's not going to work. This drawing is showing, can you all see, am I big enough up there that you can see me? Right, the first drawing is showing this. So I am holding this down. So Seamus, if you were to describe the condition that this catapult throwing arm is in, would you say it is at rest or in motion? It's at rest. Okay, so right here, this drawing where the force of the hand is pushing down and the elastic force of the band is pulling up right here, okay, the throwing arm is balanced. Leo, if the throwing arm, the forces on the throwing arm are balanced, and we're saying that it is therefore at rest, which of Newton's laws does this catapult describe in this position?
First law of motion.
The first law of motion. It states that, JD, an object at rest tends to do what? Yep, and an object in motion, JD, tends to do what? Unless acted upon by what? I can't hear you. No, what, Zach?
Outside force.
An unbalanced force, which is usually an outside force. Okay, so all right, so what you couldn't hear probably in the video was JD's JD said an object at rest tends to stay at rest, an object in motion tends to stay in motion, and then Zach said unless acted upon by an outside force, and I kind of wanted to say an unbalanced force. That's Newton's what, everyone?
First law.
Newton's first law. Okay, so right here, when I use the catapult and I pull it back, I give the throwing arm elastic potential energy. But in addition to that, okay, when the arm is pulled back, and something like it, yeah. This is the part where you're going to kind of, so you got to figure out where you've already written about the arm being pulled back, right? That's why you want to know where the stuff in your intro is. So you can nest this in there somewhere. So take a second to find where you want to write about Newton's first law in the arm being pulled back. So when the arm is pulled back and the force of my hand is pulling down, and the force of the elastic band pulls the arm up. What do we know about the forces? They're what, Nico? The force of my hand is what by the force of the elastic band? The elastic band.
Which is retaining its energy through elasticity.
Right, but what I want to know is when the force of my hand is pulling down and the force of the band is pulling up and I haven't released it yet, what is the relationship? What is the relationship between the forces? Balanced or unbalanced? Balanced because of Newton's what? We just stated it. Newton's first law. So when the arm is pulled back and the force of my hand is pulling down and the force of the elastic band pulls the arm up, the force of the hand is balanced by the elastic force of the rubber band. I know this because Newton's first law states, and you write it. We just said it. Newton's first law states is it too small? An object dot, 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 dot. This is the thing we just said, in which I can do this, I think. Yeah. An object at rest tends to blah, 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 blah. An object in motion tends to blah, 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 unless acted upon by unbalanced forces. So there are two possibilities of forces. They're either balanced or they're unbalanced.
Karen,
Yes,
out of curiosity, why do you want us to say unbalanced or to outbalance?
because outside, like, are there outside forces acting on me?
Yes.
Yes, there are. Are they all balanced? Yes, they are. I'm at rest. Gravity is balanced with the normal force of the floor. I'm not sinking through the floor, nor am I flying through the air. So if it isn't, does an outside force act on me? Yes. However, I'm staying at rest because the outside forces acting on me are, everyone? Balanced. So it's not outside forces. Often an unbalanced force is, as I said, often an unbalanced force is an outside force, but it is not always the case that because there are outside forces acting on something, that they are not balanced. Yeah. So the forces have to be what, Daniel? Unbalanced. That's what Newton's first law is about.
When
Oh, you're on to the next thing. Okay, let's give everyone time to write Newton's first law. Give me thumbs up when you've written it. You've typed it into your lab report. Got some thumbs up in here. I'm just checking the screen with my left eyeball. Shivani, not sure. Shivani has it. Ryan Crum has it. JD's typing. Seamus is typing. Nico's typing. Huh?
What happened to Maddie?
Maddie's there.
Also, what's gonna happen once you're done?
Hi,
with
Maddie.
the Catapult lab?
We're done. Hannah, did you get Newton's first law in there?
So are you planning to have this finished on the very last day of school?
No, it's everyone's gonna finish way before that. We have to have an ice cream social or something. I don't know. You got it?
Pizza. I
Yeah.
think pizza's better.
Oh, pizza and ice cream. Why? Why even choose?
Yeah,
Let's have them both.
because.
I'll bring the lactate. So we don't have like a fart festival in here.
Wait, are you lactose intolerant?
No, but I know everyone in my family is. Striking the chime for lactate. Allows us to consume cheese and ice cream. Two very important things. Okay.
Who in here is lactose intolerant?
I don't know. It's probably at least half of us, right?
I'm trying to be vegan. So it's helpful.
All right, listen up. Let's keep going. Zach brilliantly, although he's looking like you're not sure you agree with me, brilliantly anticipated what comes next. We drew it, right? So we described in this first drawing, oh, I'm not gesturing at the right things. Where's my arrow guy? There it is. Okay, we first described this being pulled down, and then we released the throwing arm, okay? As soon as the throwing arm's released, so everyone did Newton's first law, y'all pay attention, because I'm gonna ask you for stuff. As soon as the throwing arm is released, what happens to the forces, Daniel? Are they still balanced? They become what? The forces on the throwing arm become unbalanced. When forces are unbalanced on an object, it experiences what, Brooke? Yes, but what is the actual thing that it's experiencing? When an unbalanced force acts on an object, it accelerates. Yeah, that was awesome. Brooke claims, and is correct, that as soon as the throwing arm is released, the forces on the throwing arm become unbalanced, claims that we then observe Newton's second law as the throwing arm begins to accelerate. Anytime an object experiences acceleration, you know it has unbalanced forces acting on it 100% of the time. Okay, so anytime something's speeding up or slowing down or changing direction, it requires unbalanced forces. So what direction is the unbalanced force in when this is happening, Patrick? We then observe Newton's second law as the throwing arm begins to accelerate. Towards what? Or let's call that the stand. We've been calling it the stand, I think. Yeah, towards the catapult stand, because objects accelerate in what direction always?
In the direction of the stronger force.
Or unbalanced forces. Yeah.
But like if a force is unbalanced, there's one that's weaker and one that's stronger.
True. So you said towards the catapult stand, in the direction of sure. Okay. What does Newton's second law say about the magnitude of that force, Daniel. The magnitude of the force will be equal to what? So the magnitude of the unbalanced force will be equal to force equals what? Yes. So people at home that couldn't hear, he said mass times acceleration.
Equal to mass and acceleration.
Mass times acceleration, not mass and acceleration. Okay, so wait a second here. We got some other things. So what else do you need to define then? Acceleration, hold on. What did someone say? Nah. Mass? But there's another place you could actually define both of these things. Elastic force.
Use elastic potential. You need elastic force too?
It's different. It's slightly different. It's almost the same thing, but yeah, they're both in the handout. Okay, cool. All right, here we go. Add. Pardon? They almost sound the same. One is an energy given to something attached to an elastic band. The other one is the force that the elastic band puts on an object that it's attached to. Pardon? Probably not.
What's elastic force?
You do need to define a force generally. It is a what? Push or a pull on an object or substance. Extremely important.
So if we, I know I have that.
If you have elastic potential energy well defined, and you talk about elastic force, I'm not going to take points off because they literally it's very redundant. They're like the same. They're different aspects of the same condition, and so therefore, as long as you define one, we're good. Okay, so then what happens? So I pull back, I release. And what happens? Maddie Foley, what happens when I let go of this thing?
It collides with brace.
It's okay.
Just
I know you actually came up with, never mind, this whole lesson. When I looked at your lab report, I was like, oh yeah, I should teach that.
I know.
But Maddie, did you hear me? All right, somebody in the room, JD. No, Ryan Crum, I haven't asked you. Brah. I release. What happens as the last step to the throwing arm? Yeah, because it hits what? Yeah, this is the stand here. Okay, it hits the stand. So the throwing arm travels, right? Or the throwing arm moves, everyone, all right, until it hits the stand. Okay, looking at this, Ryan Crum, again, does it look like the throwing arm puts a force on the stand? Yes, it does. The throwing arm puts a force on the stand. Shivani. Does it look like that the stand puts a force back on the throwing arm? Really, watch it again. It does, right? You can see it actually knock the throwing arm that way. So it does. The throwing arm puts a force on the stand, and the stand puts a force back on the throwing arm. So Ryan HB, what is the end result of that collision right there? What happens to the throwing arm?
It springs back forward and launches that.
Yeah, and then it stops, right?
Yes.
So the stand is causing the throwing arm to accelerate, could I say? In the backwards direction?
Decelerate?
Decelerate, which is just another way of saying accelerate. If the stand is causing the throwing arm to accelerate, is it putting an unbalanced force on the throwing arm? And fundamentally, it's stopping it. Does everyone catch that? So look at this. The throwing arm puts a force on the stand, and the stand puts a force back on the throwing arm. Which of Newton's laws is this describing? Leo?
Third.
The third, okay? This is Newton's third law. This is a Newton's third law pair. The force that the stand puts on the throwing arm puts on the stand is what and what to the force that the stand puts back on the throwing arm? Equal in magnitude and opposite in direction. Yes, okay? So this stops the throwing arm. Yeah, which makes them Newton's third law pairs. The two forces are equal in what, everyone?
Opposite.
Equal in magnitude, sorry, is what I wanted, and opposite in what? Direction, okay? That makes them a Newton's what? Third law pair. Cool. So write that. I'll give you time. Something like that. Bada bing, bada boom. Direction. Yeah. And we've got, and actually what's great is for each of these things, right? For this one, I could say see figure 1, drawing on the bottom left. Right? For this one here, I could say see figure 1, drawing top left. And here I could say see figure 1, top right. Now, there are probably people that have more than just these definitions in here, but this was the thing that I noticed was absent from people's introductions most, that I wanted to make sure that we put in here, because Newton's laws are a really big part of this class, actually. Okay, so thumbs up. Everyone actually finished the statements that I dotted up here, right, in their intros. Yeah, 1, 2, 3, 4. Maddie and HB, thumbs up. Maybe. Okay. It should be the longest one you've ever written. And so that's the other thing that I'm going to say is, remember the two purposes of this lab, right? So of course, obviously you started your introduction by saying what the purpose was, right? One was to talk about or to examine changes in what's going on as the catapult operates. The other was to demonstrate that you understand everything we learned about the entire year, okay? Which is why it's such a long introduction. This is really where you show how your knowledge, like, you can use it to explain real stuff.
The other is to demonstrate what?
I can't remember. It's in the handout, actually. I don't want to misspeak because I don't actually remember. Nope, not yet. Because look, the throwing arm stopped. The two forces are blah 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 blah, equal in magnitude, opposite in direction. Okay. Now what happens to the marble? The marble, use the word launched. I love that word. The marble becomes what when it's launched?
Airborne.
It becomes launched, airborne, etc. But the science word is it becomes a projectile. Yes. In the handout for this lab, you have to define projectile. Okay. What does it retain, Seamus? What does the marble retain? What kind of energy does it keep? Yes, it becomes a projectile when it is launched in the air, it keeps its kinetic energy and its what would we say at this point? Velocity, right? It keeps keeps its kinetic energy and velocity. Now, what's interesting is be careful. Some of you have already written about this. I've been looking at the intros. Some of you have talked about the transition to a projectile, right? So what you don't want to do is accidentally do some redundancies in here. But we have a couple more things you need to define: projectile and obviously velocity. And as you see, as you build up your intro, you're actually going to end up literally explaining almost everything we've learned about this year. So let me stop sharing. And then projectiles are only being acted upon by the force of gravity. Then you define the force of gravity, et cetera, et cetera. Yes. Isn't on what? Oh yeah, it's probably elastic potential energy is all I wanted. And I just want you to talk about the force of the elastic band. Yes, you don't. Actually, we wrote the definition to it in our drawing, probably. Probably.
Would it be accurate to say that it becomes a projectile essentially due to inertia?
Because it has mass? Sure.
Because I just wrote, however, due to inertia, the object is.
Yeah, so actually, Maddie and Ryan, I have to end the Zoom, and so this turns into a video that isn't. Wait, never mind. No, I don't.